Right, let's move on to next part of the topic, which is equilibrium. When an object is at equilibrium, it means two things. Is that it doesn't. One is that it doesn't have any. It is at rotational equilibrium. Secondly, it is at translational equilibrium. Rotational equilibrium, you already understand from the previous case when we talk about moment. Is about rotation, so it does not rotate if it's at rotational equilibrium. For translational equilibrium is that it does not accelerate in any linear direction. So for example, it doesn't accelerate in the x direction, it doesn't accelerate in the y direction, or in any other direction actually. So that means to solve the problem related to equilibrium, there are two things that we need to remember. Number one is that the sum of force in any direction should give you zero, or we say that there's no resultant force in any direction. Secondly is that the sum of moment in any point must be equal to zero. No resultant moment about any point. Okay, no resultant moment about any point. So there are two ways to figure out how the forces are related to each other. Number one is that we see whether those forces has line of action that pass through a concurrent point. So for example, in this case, there are actually forces in this three direction, and they have a common point where they intersect. I mean, the line of action of these forces intersect. So that's called a concurrent point. So if we are able to find one like this, that means it should be a equilibrium case. Number two is that I have the drawing actually. So number two is that these forces can be arranged into a closed polygon. Okay, so these forces can be arranged into closed polygon. So there's two methods here that you might be applying it if you want to solve the problem. So that here's an example of a tug war. Okay, so if we rearrange those vectors of the forces, it will form a closed polygon. So not just triangle, actually it can be any form of polygon. So if it close, if it is closed polygon, then it is at equilibrium. That means they are not accelerating in any of the direction that they are trying to pull. Okay, probably they are moving linearly. I mean, they have a constant velocity, but they shouldn't be accelerating. Okay, let's look at another case here. So this is something that is leaning against the wall. Here's a smooth surface. When you say smooth surface, means that there shouldn't be any frictional force either up or down. Okay, because it's smooth, so it will be just a normal reaction force pointing normally from the surface, and it has its weight, and it will also be touching the rough surface at the bottom. So rough surface means that there should be frictional force. So on top of a normal reaction force, okay, it has a frictional force that is trying to stop it from falling, because as it fall, its motion will be here, right? So the force that prevent it from moving must be pointing in the opposite direction, which is towards the other water. Okay, so if we extend the line of action of these three forces, they meet at a point, then this thing should be at equilibrium. Okay, this thing should be at equilibrium. Let's look at another case. Okay, this one is something that is hinged on the wall here, and then it also being tied to a cable and hinged on the wall on the top there. Okay, so tension is pointing here, weight is pointing here, and let's say you are asked to figure out the reaction force from the wall at the pole. So the technique that we can use is the idea of concurrent point. So let's say you don't know where is this, and then you figure out that, oh, these two forces, they actually join here. So of course you're going to draw a line that is joining it until here. So then you know that, oh, reaction force is actually pointing here because it is at equilibrium. Okay, so let's move on to identify forces in equilibrium. So out of A, B, C, D here, based on the idea of the closed polygon just now, let's identify which three forces are in equilibrium. You can pause the video to find out the answer. Okay, so let's look at A. This go here and go here, but this is in wrong direction, so this one cannot. B goes here, but this one go here, so cannot. Let's look at C. This one go here and then go here, but this one go here, so this one cannot. All right, this one D go here, then here and here, so D is the answer. This forces in D is at equilibrium, but the other three is not. One more. You can pause the video to find out. Okay, let's look at P. P is here, then go down, then go here, so this is wrong. Q, this go here, then go here, this is wrong. R, this one here, this one here, and this one here, so this is correct. S, this one here, here, then here, so S is also correct. So R and S are at equilibrium. Okay, so this is a case that is related to calculation. So we have a lamp hanging on the wall in such a way. So these are the cable that is hinged on the wall, tied to the wall. Okay, this angle here is 90 degrees. Okay, downward force is 1960 is calculated, so we don't need this value actually. So we can arrange these three forces into a closed triangle like this. Okay, then this is 90 degrees. Here's 60 because here is 60, so with the horizontal is 60. Okay, this one is let's say T here, the W here is 1960. This one is FA and this is FB. Okay, so because it's a right angle triangle, we can apply the trigonometric rules very easily. So say for example FA, we know FA actually is the hypotenuse of this triangle, so therefore W is component of the hypotenuse that is opposite to the angle. Okay, and then for FB actually you can use tangent, that W divided by FB equals to tangent 60. Okay, so you put in 1960 and 1960, then you should be able to find the FA and FB. Okay, so next one, this one I will leave it to you as your homework that you need to submit to me. Take a picture of that of your solution, but in this case here, let's just try to analyze it. So there's a tension B and there's a tension C here. So at this point A, there are three forces. If it is at equilibrium, it should be passing through this, and there's a weight here. So we will use these three common symbols. So by this case here, he is not 90. Be careful. So we cannot use the trigonometric rules. Basically, you have to use vector resolving the TB and TC into vertical direction and horizontal direction, two simultaneous equation. Then you can find the TB and TC, the two unknowns there. Okay. Right, let's move on. Which of the following diagrams shows correctly the force F on X which would produce equilibrium? Okay, the force F on X which will produce equilibrium. That means that there's a third force on top of the P and Q. So again, back to the technique on finding the closed polygon in one direction. Okay, you can pause the video to find the answer. Right, answer should be A, because it move. I mean, when you join them, they form a closed polygon in the same direction. So but you also have to make sure that P and Q is not different from what is given here. Okay, if it's different but form a closed polygon, also cannot, but we don't have such a case here, so don't worry about that. Other case, you have to verify if there are two polygons that form in a closed triangle. Okay, let's look at this case here. So same thing, we have three forces here, TQ, TR, and W. Okay, so let's check whether they form in a closed polygon. So you can pause the video to find it out. Okay, so then you should realize that in this case there are two that go in the same direction, I mean in one direction, which is this and this. So these two are the possible one. So again, like I said just now, if this is the case, then you have to figure out whether the forces given are same orientation as what is given in the diagram above. So it seems like D is more proper because we have the TR here and the TQ that is drawn according to the diagram above, whereas A is like some of the forces are a bit different, orientated differently, so we don't accept that. Okay, right, so okay, this one again, you can try to find out which one is in a closed polygon. Okay, so C definitely cannot, because this one will produce a net force, up and down cancel, so this one cannot. These three obviously cannot because they go in about the same direction, so cannot. So it's most likely it's A or B. Okay, most likely A or B. So here we got a problem, okay, because we don't know really whether they are forming the close, okay, the idea here, close polygon. If you try to use the scale diagram and you try to draw for this 3 and 3, let's say cm, then you should know that, I mean, you can figure out that this one actually doesn't form a closed triangle. Okay, so that one has to be checked in details, but B will assure us in a simpler way, because we have 3 4 5 here and it's 90 degrees. So if we know that it's 3 4 5 according to trigonometric rules and the hypotenuse rule, you know that 3 square plus 4 square, then you root it, you become 5. So B can be quickly verified actually. Okay, so we are going to continue with this in another video. All right.